Hi, Year 10. So I'm just going to run through the long answer momentum questions with you so that you can check that you've got your answers right and you've shown all your working. So question 1, ignore the 2, sorry, says that you've got a hammer being used to drive a nail into a piece of wood. It tells you the mass of the hammerhead is 0.15 kilograms, the speed that it's travelling when it's about to hit the nail is 8 meters per second. That obviously then knocks the nail into the wood and comes to rest, and the time of contact is 0.0015 seconds. Where it says the hammerhead stops after hitting the nail, that tells you that the final velocity is 0 meters per second for the hammerhead. That's important because the first question is asking you to calculate the change in momentum of the hammerhead. Okay, so change in momentum is delta P. Okay, so that's P after minus P before. Remember, P stands for momentum. So that's mv minus mu, because momentum is mass times velocity. This is final velocity, this is initial velocity, so you're finding the change. Okay, now you know that the final velocity is 0. So this part cancels because it's all 0, and so the change in momentum is just minus mu. Okay, so that's going to equal minus, so the mass is 0.15 and the velocity originally was 8. Okay, so when you do that you'll get minus 1.2, and you need a unit because there's not one given, and it's a mass multiplied by a velocity, so it's kilogram meters per second. Okay, so the change in momentum is 1.2 kilogram meters per second. The minus just shows that it has reduced, not increased. Then it asks you to state the impulse given to the nail. That is just checking that you remember that impulse of an object is change in momentum. It's just checking that you know the definition. So if it is the change in momentum, you've already calculated it, so you just need to write the value that you got in A. Okay, so minus 1.2 kilogram meters per second. Okay, and then it asks you to calculate the average force between the hammer and the nail. Now you know that impulse, as well as being the change in momentum, it's also equal to force multiplied by time. So the force acting on the object multiplied by the time that force acts. Okay, so we know that that is equal to 1.2 kilogram meters per second. I'm just going to ignore the minus sign just for now, but just because it shows you the direction, it shows you that it's decreasing rather than increasing, but we just need the absolute value, so it doesn't matter whether you include it or not. Okay, and so if I take this phrase, I can rearrange and say F equals 1.2 over T, and I'm told in the question that that is 0.0015. Okay, and that works out to be 800 newtons, and that's my final answer for the average force for that question there. So that's question 1. Then in question 2, you've got a moving engine moving towards a stationary truck. That means 0 meters per second. That's important. You're told that the mass of this engine is 0.5 kilograms in the question, and you're told that it's moving at a velocity of 0.32 meters per second. Okay, and that's before they collide. So calculate the momentum of the toy engine before the collision. Well, P momentum is mass times velocity, and it's of the engine, so it's going to equal the mass of the engine, which is 0.5, multiplied by the velocity of the engine, which is 0.32. And when you do that, you're going to get 0.16, and again it's kilogram meters per second. Don't forget your unit there. Okay, then in the next part of the question, it also tells you the mass of the truck. I'll put that on here, that's 0.3 kilograms. Using the principle of conservation of momentum, calculate the speed of the joined engine and truck immediately after the collision. Now, we've worked out that the momentum of the moving engine before, so P before the collision, was 0.16 kilogram meters per second. And we know that the P before of the truck was 0 kilogram meters per second because it wasn't moving. So 0.3 times 0 is 0. Okay, so the total momentum of the system before the collision, if I write P total for the system that I've highlighted, it's going to be 0.16 kilogram meters per second because it's just 0.16 plus 0. Okay. Now the principle of conservation of momentum says that the total momentum of the system before the collision is equal to the total momentum of the system afterwards. Okay, so I can say that P after must equal 0.16 kilogram meters per second for momentum to be conserved. It has to be the same value in total. Okay, I know that the engine and the truck join after the collision. So what we have is an object that has a combined mass of 0.5 and 0.3. Okay, so that's 0.8 kilograms in total. And it's asking you to find the speed after the collision. Okay, so here I can say P after is equal to M after times V after, which is 0.8 V. Okay, and that must equal 0.16. Okay, because it has to total the momentum from before. So I can rearrange and say V is equal to 0.16 over 0.8. Okay, and when I do that, I'm going to get 0.2 meters per second. And that is my final answer to go in there for the speed after the collision. So that's number 2. Okay, final question. Number 3, you've got a crash test situation where you've got a dummy inside of a car being driven into a barrier. Now, a different fact that's just completely come into mind, I've been reading a really great book called Invisible Women, which is looking at statistics around the world and how women are negatively affected by things. And women are significantly injured more in car accidents, in the same car accidents as men, because crash test dummies are designed on men's bodies. And so all of the safety regulations look at what happens to a male body in the accident, and women are then injured more because their bodies haven't been tested in the same way. It's a really interesting book, side note. Anyway, back to physics. You've got a dummy that is 70 kilograms representing the person, and the car approaches the barrier at 20 meters per second. That's the speed it hits the barrier with. It stops, and so V equals 0 meters per second. The final velocity is 0 meters per second. Firstly, it asks you to calculate the momentum of the dummy immediately before the crash. Okay, so P before equals mv, so that's the mass multiplied by the velocity, where we're looking at the initial before the collision. So that's going to be the 70 kilograms multiplied by the 20 meters per second that they were initially travelling at, and that's going to give you 1400 kilogram meters per second. Okay, and that is your answer there. Then it asks you to determine the impulse that must be applied to the dummy to bring it to rest. Okay, now impulse is change in momentum. If it's at rest, it has no momentum. Okay, rest means 0 velocity, so 0 momentum. Okay, so we have to go from this value to no value, to 0. Okay, so the change has to be this amount because I have to reduce this to 0. So it's just the same number here. So again, it's just checking that you remember what impulse means. You can see a common theme here. So that's part II. Then it says, in the crash test, the passenger compartment comes to rest in 0.2 seconds. Calculate the deceleration of the passenger compartment. So this uses your motion topic from the start of the year. So we know that deceleration is just negative acceleration. Okay, so it's just an acceleration value. So I'm going to say A is V minus U over T. Okay, change in velocity divided by the time taken. So we know that the final velocity was 0, okay, because it came to rest. And we know that initially it was travelling at 20 metres per second. And I'm now told that that happens in 0.2 seconds. Okay, so I've got minus 20 over 0.2. So I'm going to get an acceleration of minus 100 metres per second squared. And that is your value here. You can list this as 100 metres per second squared because it tells you that it's a deceleration, so you don't need to put the negative sign because it's decelerating at this value. In part C, we're told that the seatbelt and the airbag bring the dummy to rest so that it does not hit the windscreen. Okay, so what that means is the change in momentum of the car is slightly different to the change in momentum of the dummy because the car smacks straight into the barrier in a certain amount of time, and that is different to the time it takes for the dummy because the seatbelt and the airbag slow that collision down. Okay, so the average resultant force applied to the dummy can be calculated using F equals ma, so using our Newton's laws now. This is the resultant force. We've just calculated the deceleration and we've got the mass of the dummy already. So that's going to be 70 multiplied by 80. Okay, because we're told the dummy's deceleration is 80. Sorry, ignore me saying 100. We use the dummy's acceleration because we're looking at the force applied to the dummy. Okay, so we've got 70 multiplied by 80 is going to give you 5600 newtons. Okay, so it's as straightforward as using F equals ma. So don't be tempted to always use Ft and change in momentum. It can be a lot simpler. Okay, so the last part of the question says the deceleration of the dummy is less than the deceleration of the passenger compartment. So the dummy or the passenger is slowing down to rest over a longer period of time than the car. So the car comes to stop first and the passenger carries on. And you have to explain why this is a benefit and why it's a safety precaution that cars have. So you're basically explaining why we have airbags and seatbelts. So we have to say firstly, it's 2 marks, so 2 points. The force on the dummy is less with the airbag and seatbelt present. Okay, so if you think about it, the change in momentum of the dummy and the car is the same. They both have to come to rest from the same speed. Okay, but remember that change in momentum is impulse, which is force times time. And if it takes a longer period of time, the force will be smaller if the t is bigger for the same change in momentum. Okay, so we have a lower force when we have a seatbelt and airbag present. So that's 1 mark. And then the second mark is for saying why that's a benefit. Okay, so don't forget to even state the obvious. Okay, a lower force means the dummy, which is the passenger, is less likely to be injured. Okay. So because it's asking for the benefit, you have to explicitly talk about the fact that there's going to be less risk of injury, not just the physics. Apologies for the banging in the background. Hope that has helped.